So I want to talk about the work that we're doing to implement quantum optimal control in the JuliaCon control organization, which has a package as the high-level framework, and then as part of that, we also have a quantum propagator package that simulates quantum dynamics. So what is quantum control? So it's basically the question of how to actively steer a quantum system in some desired way. So I think a lot of you are coming from quantum computing, and certainly all the talks you've heard today are quantum computing. So usually you're working at the level of a circuit diagram, like this from the Yao documentation that Roger just talked about, or you have packages like Qiskit or Braket that we also heard about today. But now from a control perspective, what we're interested in is how exactly would you implement one of these gates physically, like this controlled rotation, for example, right? So in Qiskit, at least in the last couple of years, they've added what they call pulse level control, and also in Braket, like Catherine talked about earlier. So that's really what we're talking about here, all right? And this really goes to the physics of the platform that you're running your quantum computer on. So for example, if you have a superconducting qubit, you'd have something like this transmon circuit, where you have two transmons with a shared transmission line, and the control that you have in this case is the field the microwave field that you put into the transmission line. And now we're going to try to find a field so that every logical basis state for the two qubit system evolves so that it implements this controlled rotation. Okay. But there's also other problems besides just implementing quantum gates. So for example, if you have trapped ions in a segmented trap, you might want to move them over some distance. And the control in that case would be the voltage that's applied to every one of these segments, and then you sort of create a trap potential that you can move to move the ion along. And you could build that into some kind of complex shuffling of atoms on a 2D chip, for example. So that's like a typical control problem. Or something that's actually closer to what I'm doing these days is you could have some trapped atoms where you split them into two trapping potentials, and then you move these potentials along two different pathways to implement an interferometer. And then you have to find exactly the right trajectory of these tractor beams to combine the wave packets again at the end. So that's all examples for quantum control. So traditionally, we've done this in Fortran. So for example, with this QDEN library that I was the maintainer of during my PhD. And Fortran is really a very nice language for the kind of numerics that you have to do here. But there's kind of two problems with Fortran. So one is just the workflow. So you end up just writing Python scripts usually for the modeling, like you use Qtip or something, and then you write out data and you write config files. So there's a lot of files on disk. And then you run your Fortran program, and then you do your analysis in Python again. And there's just a lot of overhead with managing all of that data. And the other problem is flexibility. So once you have like a really big library, you want to do something new maybe that doesn't really quite fit into the existing data structures. And then things just get more sprawling and complicated in the code. So that's definitely a problem. So you might just start out with basic energy levels, like for the transmon, but then you also want to do molecular dynamics or molecular rotations or spin systems, and then you have to just manage all these different data structures and code paths. So we also tried to port some of those optimization methods to Python, and that works pretty well as far as the optimization itself is concerned, and it definitely makes the workflow easier because you can do that in Jupyter notebooks. But the problem is that for the underlying simulation of the quantum dynamics, the performance just isn't there. And on top of that, you have the GIL in Python, so the global interpreter lock, and that really kills the kind of parallelization that you'd like to do for this type of thing. So then you have to start doing something like Cython, and that just gets very technical and sort of very annoying, and then you run into sort of all kinds of packaging and compilation problems. So it's really not a lot of fun. And on top of that, really neither Python nor C really have very good semantics for the kind of numerics that we want to do. Okay, so why Julia then? So the first aspect is definitely flexibility, and that was sort of the original motivation for me. So compared to Fortran, you have a much nicer workflow. Again, you can do it in notebooks, but you also have multiple dispatch to solve the problem that you want to do sort of unusual things with custom data structures that are sort of particular to the physics of a given problem. So that just separates extremely well in Julia.
And then, of course, the second aspect is performance, especially compared to Python. And that really becomes relevant for open quantum systems or noisy systems. So not really the examples I show later in this talk, but sort of the actual sort of research systems where the optimization might actually run for several weeks on a cluster. And it's really not something that you can scale Python to. And then last but not least, Julia also has really nice expressiveness compared to both Fortran and to Python, with a real focus on linear algebra and Unicode and things like multiple dispatch. So it's really a very pleasant language to work in for these kinds of problems. Okay, so let's just jump into an example. So this is something that I've adapted from one of the examples in the documentation, and I go into some of the details and the design principles of the quantum control package as we go along. So the example is just going to be the same one that I mentioned before, which is these two superconducting transmon qubits coupled to a shared transmission line. And just for simplicity, I'm going to assume that what's called the dispersive limit, where the coupling between the qubit and the cavity is relatively small, so you can adiabatically eliminate the cavity. And what you end up with is the microwave field that you put into the cavity here that ends up effectively driving the transitions of the qubit. And then on top of that, you also have a static qubit-qubit interaction between the two qubits. So the energies of these qubits are on the order of gigahertz, which means that there's a time scale of nanoseconds. And we're going to truncate the levels of this qubit to 6 levels. So that means that the dimension of the total Hilbert space is going to be 36, which is not too big, but it's also not completely trivial. Okay, so now we can write out the Hamiltonian. And well, the first thing we're going to do is we're going to go to a rotating frame, which means that we shift the qubit frequencies down by the driving frequency. And the other thing that does now, now the control field is going to be complex, where the complex phase of the field tells you the deviation from the drive frequency. Well, and beyond that, now we can just write out the Hamiltonian sort of in a very straightforward way that basically looks like you would write it on paper. So we have this anharmonic Duffing oscillator for the two transmons here and here. And then we have a static interaction term there. And for the control term, we want to treat the real part and the imaginary part of the control as two independent control fields, just because the control kind of at the control level always has to be a real valued function. So we split that into two terms. So let me just talk about this Hamiltonian function that I'm using here. So the underlying concept that's really pretty central to the quantum control package is that of a dynamical generator, which is the object that describes the dynamics of the state. So it's the time-dependent Hamiltonian or the Liouvillean. And mathematically, that structure is that's most directly supported is this equation here, where you have a drift term, and then you have control operators that get multiplied with a control amplitude. And then that control amplitude can depend on one or more control functions epsilon, and the epsilon is what you directly manipulate with the optimal control. Right? So that's what you change, and then the amplitude is going to be on top of that. So in many cases, the control amplitude is actually just directly the control function, and then you get this linear control Hamiltonian down here. But in general, you could have an amplitude where maybe you add noise on top of your control, or you have something that depends non-linearly, like maybe a spin-orbit coupling that's quadratic in the field, or you have some transform function in your waveform generator where the thing that comes out isn't actually what you put in exactly, or there's really a lot of other things you could use for this amplitude versus the actual control. So it's really quite flexible. And the call to the Hamiltonian gives you exactly the structure where you give it tuples of control operators and control amplitudes. But in fact, you could be even more general. So you could have an operators that depends in some completely arbitrary way on any number of control functions, maybe like element-wise sort of controls inside of your Hamiltonian. So ultimately, we just have an abstract interface for what you're allowed to use as a dynamical generator. So basically, you have to be able to extract controls, which are just scalar functions or arrays, because otherwise you don't have anything to do the optimal control on, right? So there needs to be like a notion of what is a control. And then you have to be able to evaluate your generator by plugging in values for the controls, and also at a particular point in time. And that has to give you an operator, and the operator has its own interface, but it's basically just an object for which you define all the linear algebra operations. So basically, you just have to be able to apply it to a state, right? So you have to implement like the mul function for that. So the important takeaway is that the quantum control package is not a modeling framework. And what I mean is that in something like quantum optics, like we heard today, you have data structures that are specific to the physics of the problem, right? So you have like position operators or momentum operators or Gaussian states or anything like that. And that's not something that you would have in the quantum control package. But the idea would be that you can take these data structures from quantum optics or other packages, or maybe something like a matrix product state or anything else that you might have, and then use them as components of the dynamical generator in the quantum control together with the control functions and the control amplitudes. And I guess the caveat is what Ashley talked about this morning is that there's this new time dependence in quantum optics, which actually looks to me like it's almost one-to-one with the interface that I just described. So that should be quite compatible. All right, so let's get back to the example and talk about the initial guess for the driving field. So this is going to be an example of what I just talked about, so the distinction between a control amplitude and a control field. So physically, what we want to have as a control amplitude, as sort of initial guess, is something that switches on from 0 to 35 megahertz, and then stays constant for about 400 nanoseconds, and then switches down again. And we're going to separate that into a shape that's just going to stay fixed, so the optimization isn't going to touch it, and the shape is just going from 0 to 1 and stays at 1 and then goes down again. And then we're going to multiply that with an arbitrary control function, and initially that control function is just going to be a constant 35 megahertz, right? And we're also going to assume that we're at the driving frequency, which means that the imaginary part initially is going to be 0. Okay, so now we can instantiate that, and if you plot it, you can see that's exactly what I just described. Okay, and so now we can instantiate the Hamiltonian based on that. And now for the states, so for the states we have a logical subspace of the two lowest levels for each of the two qubits, so that's going to be the 0 and the 1. But then we have additional levels on top of that, which we truncated to 6, and we'll tensor that into a logical basis for the 2-qubit system. And if we look at just one of those states, we'll see it's a 36-dimensional vector. It has a 1 in a particular place and 0 everything else. So it's like a padded sort of 2-qubit state. Okay, so let's look at the dynamics of the system. So we're going to use this propagate function, and this function is what simulates the time dynamics. So we have the Schrödinger equation, or we have you have the Liouville equation if it's an open system, which is actually the same equation, with some number of control fields, which we call epsilon and L, so that's like the real field and the imaginary field. So why not just throw this into differential equations, or use the dynamic solver from quantum optics, or something like that, right? So there's many packages that can just simulate this Schrödinger equation. So remember that we're going to change the control fields via the optimal control, right? And if you want to have a control procedure that really gives you arbitrary control functions as an output, then pretty much what you have to do is you have to discretize it to some time grid. And then the standard thing to do is just to take the controls and assume that they're piecewise constant on that time grid, right? So using a small time grid here. And then the optimum control will just tune the values for the field at the different points in time. So now actually you don't actually have to solve this differential equation as an equation, but you actually know analytically what the propagator is going to be, and it's just e to the minus I h dt for any particular time slice. And now you can just evaluate that by expanding the application of that propagator into a polynomial expansion. So think something like a Taylor series, but in fact a Taylor series is actually a very badly converging series. So instead, you can use Chebyshev polynomials if the generator only has real eigenvalues, because Chebyshev polynomials are only defined on the real axis, or Newton polynomials, for example, for an open quantum system, if it's a non-Hermitian generator. And again, all of this is implemented via an abstract interface. So you can implement propagators where all you need is an init prop function that sort of sets up the thing that holds the state of the propagation, and then you step through the time grid with a prop step function. And the Schrödinger equation is implicit in this, but if you have something different, like maybe a Gorz-Pytayevsky equation or something like that, you could define your own propagator just according to that interface. Okay, so let's get back to the example. So we're going to be interested in what happens with this system in the logical subspace. And we're going to define this observable, where we take the overlap of the state that we're propagating with every one of the logical basis states, right? So that tells you what's going on in that logical subspace. And so we're going to propagate all of the basis states. So if we do that for all of the basis states, because we have this parameter storage equals to true, what you're going to get out, just for sort of the last of them, it's a matrix of the complex projections at every point in time. And now we can just concatenate that to get a 4x4 matrix at every point in time. So that's the gate that you got in the logical subspace at every point in time. Okay, and well, now in order to analyze that, we're going to use something called a gate concurrence. So gate concurrence is just a measure of how much entanglement you can get if you apply the gate to some specific separable input state. And probably the most well-known perfectly entangling gate is a C0 gate, and we can indeed verify that if we calculate the gate concurrence for a C0, that we get 1. Okay, so now if you look at the gate concurrence for dynamics, so how much entanglement are we generating? We see that it starts at 0, because obviously at 0 the gate is the identity, but then it fluctuates a bit, and then but it only goes to around 78%, and so it's not a perfectly entangling gate. And the other thing that we should look at, because we have these extra levels in the transmon, is the loss of the population from the logical subspace. So we can just plot a unitarity measure here, and we see that we end up, we lose about 10% of the population from the logical subspace at the end. Okay, so now let's do an optimization where we maximize the gate concurrence. So we're going to define these objectives. So these are also pretty central to the quantum control package. So these objectives just tell you which states should the optimization look at and how should they evolve. And in many optimizations, you have something, you have a target state in there. But here it's actually a little bit more general because we're maximizing entanglement. So there's no specific target state. So we just have an initial state, and then we have the Hamiltonian in there as the generator to tell you how the state should evolve. Okay. So now we're also going to define an actual functional that we're going to minimize. And that functional is going to be the combination of the gate concurrence and the unitarity. So we're going to minimize the loss from the logical subspace while we're maximizing the entangling power. So this functional should be 0 in the optimal case. And we can check that for our time evolution, it's still pretty far from 0. And just for formal reasons, so this functional that I defined there, it's a function of a 4x4 matrix. But what we actually need to give the optimization routine is a function that takes the propagated states as input. So we just have this gate function routine here that does that conversion. Okay, so now I actually kind of skipped over how we actually minimize the optimization functional. Right? So remember that we've discretized the control field to be piecewise constant. So our control parameters are the values of the different controls epsilon L at different time slices n. And what we want to do is we want to change the values of epsilon and L in the direction of the gradient of the functional with respect to that particular value, right? So it's a gradient-based optimization. So you just change your field in the direction of the gradient. And now our functional is, so functional is basically the gate concurrence. So how is that actually calculated? Well, so for any 4x4 matrix, what you do is you take this partially rotated matrix utility, and then you calculate these values, C1, C2, C3, from the eigenvalues of that product. And so these C1s and C2 and C3 are called wild chamber coordinates. And then you can get the gate concurrence by looking at all the possible combinations of the C1, C2, C3, and finding the maximum of this sign. But just from the fact that you have to calculate eigenvalues, it's not something where you have an analytic gradient, right? You can't just write down the derivative of this procedure. So something that people like to do now is to just do automatic differentiation. But what that would actually mean is that you would have to do the entire propagation inside of an AD framework. And that means that you're going to be building a computational graph. And that's a huge computational graph that's just totally going to explode your memory. So that's not really practical for any kind of larger Hilbert space or a lot of time steps or anything like really difficult. So instead, what we came up with is this idea of semi-automatic differentiation. So let's just very briefly go over what that means. So this is the gradient that we want to calculate, right? So derivative with respect to the control values. And now we're just going to formally write the functional as depending on the propagated states. So that would be the 2 qubit bases in our case. And then we can do just a chain rule. And now this derivative of a scalar with respect to a column vector, that's going to be a row vector, and we just call that bra chi. And now we're going to pull out that derivative with respect to the controls forward. And then this whole thing just turns into a gradient of the overlap between that state chi and the propagated state psi. And the gradient of an overlap of 2 states, that's actually something that's very well understood numerically. So there's a pretty straightforward existing scheme, and basically what it comes down to is you forward propagate the psi, you store all the propagated states for every point in time, and then you do a backward propagation of that chi, and then take the overlaps at every point in time to get the gradient. So it's a very sort of standard scheme and well understood. And for the details of that, I would refer you either to the paper or to this talk that I gave a few months ago. And that also includes the benchmark to show you how a direct AD doesn't really scale numerically. Okay, so let's get back to the example. So we're going to use this functional make gate chi, and that's going to do exactly what I just described. So it's going to use automatic differentiation to calculate the chi that is the derivative of the functional with respect to the state. And you see here that the output is some function that involves zygote. That's where the AD comes in. Well, and this is and with this we can just set up the control problem. So the control problem is just going to be the list of objective. So it's the states that we want to look at and the Hamiltonian. And we give it a time grid. We give it the optimization functional. And we give it this chi state that we just constructed with automatic differentiation. So that's going to be part of the gradient. And then we're going to give it a rule for when we want to stop. Okay, so now we can just run this using this optimize function. So I'll just call that. And we see the optimization sort of slowly converging to 0. And in about 5 seconds or so, we end up with an optimization result. And now we can plot the optimized field. So you see that you get these oscillations here that you didn't have before. And I guess we can also look at the dynamics under that optimized field. So we're going to extract the original controls from the Hamiltonian using this getControls function. And now we're going to construct a new Hamiltonian where we just substitute the guess controls with the newly optimized controls from the result object. And we can propagate that in the exact same way as before, so and extract the 4x4 gate at every point in time. And now if we plot the gate concurrence of these new dynamics, we see that if we compare it to the guess pulse, we end up now with a gate concurrence of 1, so we have a perfectly entangling quantum gate. And also if we look at the loss from the subspace, we see that it's still going to oscillate, but now at the end it's going down basically to 0. Right? And that's all for the example. So now what about performance? So as I showed before, so one evaluation of the gradient requires 2 time propagations over the entire time grid. So the numerical cost of the optimization is really identical to the cost of just simulating the dynamics. So this is the runtime for simulating dynamics for 1,000 time steps for a Hilbert space dimension of 1,000. And the baseline that I'm showing here is the Fortran code that we were using previously. And with Fortran, it actually matters quite a lot which compiler you're using. So if you're using a commercial compiler like iFort, you might actually get something like a full factor of 2. Okay, so now what about Julia? Well, we can see that Julia matches the performance of the Fortran code with iFort. It's actually even a little bit better, but just a few percent. But then there's also the flexibility of Julia that you can just, you can use different data structures. So for example, you could use a GPU data structure and make this entire propagation run on the GPU, and you almost get a factor of 3 in performance. And I didn't rewrite anything for this, right? So I've never done GPU computing before. So the only thing I did is switch out the regular arrays with GPU arrays. And similarly, if you use sparse matrices, so in Fortran we have our own implementation of sparse matrices, but then in Julia you have it built in, right? And it turns out, well, apparently the people who implemented sparse matrices in Julia are better programmers than me because it's twice as fast. Or if you go to really small Hilbert spaces, so this is a Hilbert space dimension 10. So there Julia, again, matches the performance of the Fortran code. But then in Julia, you also have static arrays, right, which are designed to work with really small vectors. And again, you get an additional factor of 2 just to do that. OK. And this is actually a surprise. The reason I started to use Julia was mainly for the flexibility. And we thought that maybe if you get a factor of 2 compared to the Fortran code, that's already a win because it makes you more productive. But it turns out that Julia is actually faster than Fortran. OK, and so I guess I still have a few minutes left for some conclusionary remarks. So let me just look at the quantum control framework just beyond just us rewriting our Fortran code and getting a nicer workflow, and talk a little bit about how this would interact with the other packages. So the one thing that's quite unique about Julia is really how multiple dispatch allows you to really separate the core algorithms from sort of the incidental surrounding structures, right? And we have that at different layers. So the implementation of the optimization method is separated from the time propagation, so you can just define your own methods for simulating dynamics. And the time propagation, again, is separated from the structure of the Hamiltonian, so you can model your physical system in any way you like, right? So the only thing we impose is really the notion that there has to be something that we can identify as this is the control, because otherwise you don't have anything, to do optimal control on. And all of these different interfaces, they're really fully specified, and we have a function that checks that a given object implements that interface correctly. So we would certainly like to interoperate with other packages, right? So if you have modeling structures like quantum optics, you should be able to use those. Or if you have special solvers, maybe for open quantum systems, you should be able to wrap that in the propagator interface. Or if you have an implementation for other methods of quantum control, then it should be possible to make that work with this optimized function and with the way the control problem is defined in this library. And obviously, if you're an author of a package like that, I'd very much like you to get in touch. Right, I could, I guess, also, since it's still only 26 minutes, I could say maybe a little bit about sort of things that are planned. So I talked about controls that are basically piecewise constant, and that gives you the most general kind of control that you could possibly have. But in practice, there's also a lot of value in if you have more constrained controls in the lab, you might have controls that actually only have a few free parameters. As you would move from piecewise constant pulses to parameterized continuous controls, and then you don't actually have piecewise constant propagation, but you could actually just use differential equations as the propagator. And there's also specialized quantum control methods like that. So if you're in the field, there's like CRAB or GROUP or GOAT. So these are definitely things that should be implemented at some point soon. But of course, the drawback of this is then if you constrain your pulses, then you end up also with local traps and controllability issues. But that's just something we'll deal with. Okay, and I think with this I'll stop, and we still have some time for a question or two.
Yes, we have a few minutes left for questions. Oh, there it is. So yeah, does anybody have questions for the speakers? Yeah, so thanks for the great talk. I'm mostly curious about the local traps aspect. So regarding global optimization, for example, I mean, there's a bunch of schemes out there. So what stops you really from doing that? Is it just that you essentially
from doing like the
like
a few parameters?
Exactly. If you have a few parameters, and then you do global optimization over them.
No, nothing stopped. I mean, it's just that. So usually, I've been interested in sort of like I give you a system, and I want to know like what is the shortest time that you can realize a gate in or something like that. So then you really don't want to put constraints onto your control. So it's sort of a different. It's more like a controllability mindset. If you have more of a mindset, I'm in the lab and I actually have constrained pulses, then yeah, you might want to do that. But I just haven't gotten around to it. Basically.
Okay, fair enough. Yeah. Okay, wait, more questions back here.
Yeah, thanks. This is awesome. So like one question on like so you got it look like a pretty, like it converged to a solution. So that was a solution with the, like not the full matrix exponential, but with like the Chebyshev polynomials?
With the Chebyshev, yeah.
How does like the fidelity with like those, like how does the fidelity transfer from like the approximate to the matrix exponential to like the matrix exponential when you roll out with that?
Oh, it's exact to machine precision.
Exact.
So Chebyshev is exact
Okay.
to machine precision, yeah. So there's no, the time evolution is completely separate from the control. You get exactly the same solution with a different control, with a different propagator.
Cool, so we're at time, and to give our next speaker their full 30 minutes, we'll thank Michael again for the awesome talk.